Hi, hello. This is Sarat Raju, Dr. Sarat Raju, Department of Mechanical Engineering. So in today's class, I am going to discuss about fluid mechanics properties, fluid properties. So in previous sessions, we discussed about what is mass density, weight density, and surface tension. Then what is specific gravity. So in this session, I want to discuss about surface tension of a hollow bubble as well as liquid droplet. In the previous session, we covered surface tension of a liquid droplet. So now I am going to explain about surface tension of a hollow bubble as well as liquid jet, and also what is compressibility, how it is important for fluids. Then what is the vapor pressure? The other property of the fluid is vapor pressure. So one by one we will see. So the course outcome of this particular topic is relate the basic properties, various types and patterns of fluid configurations. So under which we are under basic properties we are discussing. Then what are the various types of the fluid patterns and fluid flow configurations that are encountered in fluid flows. So surface tension of a hollow bubble. In the previous class, we discussed a liquid jet for liquid droplet. So for the liquid droplet, we derived an expression sigma equal to surface tension of the liquid droplet equal to PD by 4. Now, what is the surface tension of a hollow bubble? So hollow bubble means you can take an example of soap bubble. So we can take the soap bubble. If you observe carefully, soap bubble inside there will be air. If you observe carefully, only a small layer, a thin layer will be formed, and inside which the soap bubble, air will occupy inside the soap bubble. Outside is also atmospheric pressure. So that is why a hollow bubble like a soap bubble in air has two surfaces in contact with air. So when you take a soap bubble, which was generally used by the children, right, in circus or somewhere they will buy, and they will blow the soap bubbles, right? So if you observe carefully, so inside air, inside also air, as well as outside also atmospheric air. So in both the cases, because the soap bubble is having a small thin layer, so it will have, this layer will have two contacts with the air. So that is why one is inside and other is the outside. Thus two surfaces are subjected to surface tension. So in such cases, we can write what is the pressure acting on the soap bubble. So pressure into, because pressure is acting on the area, already we discussed in case of liquid droplet, pi by 4 d square. And also what is surface tension? Surface tension is sigma into, because surface tension is always acting on the circumference of this one. So if you break it, we already saw in case of liquid droplet, this on the surface, on the circumference only, this surface tension will act. But whereas pressure is acting on the surface area of the surface. Suppose if it is a hollow bubble or this thing, if it is in the form of a sphere, if you cut it, make it into two halves, so this is the area, surface area of the liquid droplet. So area, that is why on area the pressure P will act. So that is why under equilibrium condition we equate both pressure force as well as the surface tension force. So that is why P by pi by 4 d square. Pi by 4 d square is the area, whereas pi d is the circumference, right? Circumference of the circle. So that is why pi d. So why we wrote 2 here? Because on the soap bubble, inside is also air, outside is also air. So this is the layer which will expose to 2 surfaces. So that is why 2 air surface. So that is why 2 we wrote. There are 2 air surfaces as well as, that is why we wrote 2. 2 into sigma into pi d. So if you equate under equilibrium condition, if you equate it, pi gets cancelled, d square and d gets cancelled, right? So P into this 2, right? Again, pi by 4, right? P into pi by 4 into d is equal to 2 into sigma. Pi gets cancelled, d also cancelled. Now PD is equal to 8 sigma, or otherwise sigma equal to PD by 8. So we wrote here P equal to 8 sigma by d, or otherwise sigma equal to PD by 8. So what we observed, in case of liquid droplet, we can write sigma equal to PD by 4. In case of hollow bubble like soap bubble, sigma, surface tension acting on the soap bubble, is PD by 8. Now we will go to the next stage, so or the next case, which is a liquid jet. So we are talking about surface tension. Surface tension definition also we have seen. What is the surface tension? There are 3 cases. First one is liquid droplet. Already we saw sigma equal to PD by 4. And in case of hollow bubble like soap bubble, PD by 8. Then what will be the surface tension in case of liquid jet? So where do you get the liquid jet generally? So this liquid jet is simply a gardener will get the water from a pipe, and he will keep watering for the plants. So the water coming from the pipe, we can call it as a jet, or otherwise in case of nozzles we can have a jets, a liquid jet which is coming from the nozzle, right? So this jet has, how, if you say this is the jet what we have taken. So having a length of L, and this is the diameter of the liquid jet. So if you make it into 2 halves, so if you observe carefully here, so these arrowheads are sigma, surface tension, right? So this, if you break it into 2 halves, the liquid jet will like this, right? Liquid jet is like this. So it is make it into, then so on the surface where we cut on the circumference, we can have cutted portion, we can have surface tensions, right? Surface tension is always acting on the circumference or outer line of the liquid jet. So that is why we can see surface tension of the liquid jet. Consider a liquid jet of diameter d, what we have shown in the diagram, and length L as shown in the figure. Let P be the pressure intensity inside the liquid jet. It is always above the outside pressure, and sigma, surface tension of the liquid. Then consider the equilibrium of the semi-jet we have. So what are the different forces? The pressure force as well as the surface tension force. The other force is surface tension. What is the pressure force? Pressure P into area of the semi-jet. Why we are taking complete jet, and we can make it into two halves, right? One half as already I shown in the diagram, right? Then what is the pressure into length into diameter? Length into diameter. So the length of the jet, right? Then this is the length. Then diameter is the diameter of the semi-jet. Okay. So that is why P into L into D. P into L into D. So what is the other force acting on the semi-liquid jet? Surface tension, because of the surface tension. So surface tension into what we have shown in the diagram, right? These are the these arrows are on the length only, on the length side. So that is why it is the periphery or the circumference, outer line of the semi-jet. So that is why we wrote sigma into 2L. Why? On both the sides it is acting. L and L. That is why we wrote 2 times L. So that is why under equilibrium conditions we can equate pressure force as well as surface tension force. Pressure force is P into L into D. Surface tension is because of the lengths, right? On the line force, right? It is of line force. Then sigma into 2L. So this LL gets cancelled. So P equal to L gets cancelled. P into D is equal to sigma into 2, or sigma equal to PD by 2. So this is the equation for surface tension of a liquid jet, the surface tension on a liquid jet. So what we have seen, so like surface tension of a liquid droplet is sigma equal to PD by 4. Surface tension of the halo bubble, soap bubble, is PD by 8. Whereas surface tension of the liquid jet is PD by 2. And also I want to take the practical example which we generally observe. The surface tension is, suppose you might have studied in intermediate or somewhere, right? Where the surface tension topic. So when soap, how we can remove the dirt particles or dirty particles from the clothes by using some detergent soap. Suppose if you take the case of a shirt which is having some mud or some oil drop on the shirt, how can you remove that? Suppose if you simply inserting or dipping inside the water, if you dip the cloth inside the water without soap, it will not go, right? So after applying the soap, it will create some bubbles, right? Soap bubbles. And because of the surface tension only on the surface of the cloth, what we are having some dirt, that can be removed by surface tension. And also I have kept one diagram, one figure, which is at the introduction, at the first slide. So if you observe carefully, so this is the insect, or sometimes even mosquitoes also walk on the water. If you observe carefully, how these mosquitoes will walk on the water or floating over the water. So this is also an example for surface tension, right? So to day-to-day life, there are so many applications of surface tension, right? One is you can remove the dirt particles from the clothes by applying the detergent soap, or even while bathing also, if you apply a soap, right, any soap, any type of soap on our body, so whatever may be the sweating or the dirt particles that can be removed because of the surface tension. And also if you observe on the surface of any lake or any somewhere where the stagnated water is there, on that some mosquitoes are kept or are there so that it will float, or sometimes these mosquitoes or insects can walk on the water. So this is also because of the surface tension. Then what is compressibility? What is the importance of compressibility? Compressibility is also one of the fluid property, right, which is important. If you take the case of thermodynamics, there will be compressible and incompressible, right? Compressibility. So how we can compress the fluids, gases, in case of either petrol or diesel, or sometimes in case of air compressor, air also can be compressed. So what do you understand by compressibility, right? So it is defined as the change in volume due to change in pressure. Change in volume, delta V by delta P. This is the ratio of, or it is defined as change in volume due to. So that means because of applying some pressure on the gas, how it can change its volume. So that is why it is defined as the change in volume due to change in pressure. Change in pressure. The property by virtue of which fluids undergo a change in volume under the action of external pressure is known as compressibility. The property by which virtue of fluids undergo a change in volume, right? Some change in volume. Why? Because under the action of external pressure or some external force, pressure force, is known as compressibility. So where there is a change in volume because of the change in the pressure, we can call it as a compressibility. Then elasticity of fluids is measured in terms of bulk modulus of elasticity K. How can you define the bulk modulus of elasticity? It can be defined as the ratio of compressive stress to volumetric strain. Volumetric stress to volumetric strain. Compressive stress is the ratio of compressive stress to volumetric strain. So compressibility is the reciprocal of bulk modulus of elasticity. That is why if you want to calculate or if you want to understand the basic definition of compressibility, if you know the bulk modulus, if you reverse it, reciprocal of bulk modulus of elasticity is known as compressibility. You can see here the compressibility of a liquid is inversely proportional to the bulk modulus. That is nothing but volume modulus of elasticity. Bulk modulus of a substance measures resistance of substance to uniform compression. What is volumetric strain? Right? Change in volume by change in volume divided by original volume. Original volume is, so change in volume by original volume. Change in volume is dV. The original volume is V. So that is why volumetric strain is the ratio of change in volume by original volume, and it is also having a negative sign. Bulk modulus K is the ratio of increase of pressure. Why it is increasing? Because by applying or by increasing the pressure, by applying some pressure, there will be a change in the volume. So that is why volumetric strain, change in the volume is taking place. So that is why bulk modulus is increase of pressure divided by volumetric strain. But what exactly we need? Compressibility. So compressibility is 1 by K. What is K? K is bulk modulus. So reciprocal of bulk modulus, we can call it as compressibility. That means what how we can write compressibility? Minus dV by V divided by dP. Right? So By taking some diagram, we can explain how this compressibility will change with respect to the change in volume by original. So this is the original volume. So that is the volume, right? Or otherwise we can say stroke in case of thermodynamics. Stroke, that is the maximum distance traveled between the top dead center TDC to BDC. So this is a stroke length, or that you can call it as a volume. That means the maximum volume occupied by the gas, or sometimes it may be liquid gas inside a particular volume. So this is the maximum travel of the piston. This is piston. The maximum travel of the piston. This is it will come somewhere like this. So within this we will have some volume. So that is, we can say this is the original volume. What will be the change in volume? Suppose the piston is traveling from this blue color to this black dashed one. So it is traveling, or it is changing a distance of dV. So it is changing a distance of dV. So or it is dl, we can say. If it is a length is L, you can say a dl, small change in the position of the piston. That means if you are applying some pressure, so pressure is here on the top. If you are applying a pressure, it will change its position. So that is why what exactly this bulk modulus or compressibility is change in volume by change in the pressure. So that is why here, because of applying of the pressure, there will be a change in the. So this dV by V, we can call it as a strain, volume strain. Right? This is the volume strain. This is in the form of a graph. This is volume strain, and this is the stress or the pressure force. What is stress? Stress, already you know the basics. Force by area. Force by area. Or what is this force? Pressure force. P by A. P by A. Stress. This is the P by A. Right? Then the other important property of the fluid is vapor pressure. Vapor pressure. So what is vapor pressure? Just I want to give a practical example of vapor pressure. So generally in villages, in olden days, we are using, they used small pots or small vessels, and by keeping some lid or some plate on the vessel. So if you keep some dal or rice inside the vessel and keep on giving some heat, so at a particular time it will water will, so in the vessel there will be some dal or rice here, and water level may be somewhere here. So if you are giving some heat, so the water will boil slowly and converted into vapor. And what if you observe practically, so you keep some lid or some plate on this, so this water vapor is trying to lift the plate up, right? So that is why in between the plate and the inside, what contains inside, it may be a rice or it may be a dal, whatever may be, in between there will be some gap. So in that, a partial pressure of vapor is applying on the contents. So that is why it is known as vapor pressure. Vapor pressure. So take the case of example of pressure cookers also. Pressure cooker. So if you observe, so if you take a normal vessel, if take say suppose 20 to 25 minutes for cooking a rice or dal, but if you take the pressure cooker, it will complete by 8 to 10 minutes. So why? Because the melting point of the water will reduce because of the vapor pressure. That we are going to see here. So what is vapor pressure? A change from the liquid state to gaseous state, that is vapor, is known as vaporization. So when the liquid is changing from the liquid to gaseous state is known as vaporization. The vaporization which depends upon the prevailing pressure and temperature condition. So it is always depending upon the pressure and temperature. Occurs because of continuous escaping of molecules through the free liquid surface. Suppose if you are not keeping any plate here open to atmosphere, so these water molecules or vapor molecules are escaped from free liquid surface. So consider a liquid which is confined in a closed vessel. Let the temperature of the liquid is 20 degrees centigrade and pressure is atmospheric. So take the case of atmospheric pressure only, 760 mm of Hg. This liquid will vaporize at 100 degrees centigrade. Right? Initially it is at the liquid normal temperature is say 20, 22, 24 sometimes. So say take 20 degrees. If you are giving some heat, so what will happen? It reaches to the 100 degrees centigrade and the vaporization will starts from say 80 to 85 degrees centigrade. At if it is reached 100 degrees, so almost the liquid gets converted into vapor. Vaporization takes place. So the molecules escape from the free surface of the liquid. These vapor molecules are get accumulated in the space between the liquid surface and top of the vessel. Suppose the top of the vessel means if you are keeping some plate. These accumulated vapors exert a pressure on the liquid surface. So in between the plate and the vessel, so which you are keeping some plate, this is the vessel say. So the partial pressure or these accumulated vapors. Suppose if you are not keeping this plate, the vapor will go into the atmosphere. But if you are keeping some plate, so this vapor is again accumulated in between the plate and the which are having some container, right? Which is having some container. Inside the container, it carries some dal or rice. So these accumulated vapors exert a pressure on the liquid surface. So the partial pressure which is acting on the liquid surface in between the plate and on the surface of the liquid is known as the partial pressure acting on the liquid surface is known as vapor pressure. So suppose take the case of pressure cooker just now I told. So take this case and what will happen in case of a pressure cooker, we will see. Again consider the same liquid at 20 degrees centigrade, and also at atmospheric pressure in the closed vessel. If the pressure above the liquid surface is reduced by some means, suppose if the pressure in between the top plate and the on the liquid surface, in between the liquid surface and the plate, if you reduce that pressure by other some means, the boiling point or the boiling temperature will also reduce. So if the pressure is reduced to such an extent that it becomes equal to less than the vapor pressure, so whatever may be the boiling temperature will also reduce. So because of that, pressure is reduced to such an extent it will becomes less than or equal to vapor pressure. The boiling point of the liquid will start through the temperature of the liquid is 20 degrees centigrade. So what will happen? The boiling point of the temperature will reduce. So at 20 degrees centigrade only, in case of pressure cooker, that will happen. At 20 degrees centigrade only, the water will boil. So that is why? Because you are reducing the pressure. If the pressure is reduced to such an extent, it becomes equal to or less than or equal to vapor pressure. then what will happen? The boiling point of the liquid will gets reduced. So the boiling point will start through the temperature of liquid is reaching, though it is 20 degrees, the boiling will start. So that is why the boiling point of the liquid is reduced. Now consider a flowing liquid in a system. If the pressure at any point in this flowing liquid becomes equal or less than the vapor pressure, the vaporization of liquid starts. So the bubbles of these vapors are carried by the flowing liquid into the region of high pressure where they collapse. So this will happen in case of turbines and pumps. So this is one of the cavitation. In case of cavitation is one of the unwanted thing in case of turbines and pumps. This cavitation is because of this vapor pressure. What he is explaining is, so when the fluid is or the liquid is in flowing, if the pressure at any point reaching a pressure equal, less than or equal to vapor pressure, less than or equal to vapor pressure, the vaporization of liquid starts. So that is why when vaporization starts, some liquid bubbles of these vapors are carried by the flowing fluid. So sometimes the liquid bubbles will form and those bubbles will carried by the flowing liquid. When they reached where a high pressure zone, they will collapse, bubble will burst, and some impact will be happening on the when it is traveling in the pipe, or when it is some parts of the turbines like draft tube or runners, right? And in case of pumps, when it is impeller or it is a inlet valve or inlet pipe or outlet pipe, see, this will happen. So the impact of high impact pressure will be taking place in case of turbines and pumps. So these are the these all the topics are taken from some R.K. Bansal and Modi and Seth, Fluid Mechanics and Hydraulic Missions by R.K. Bansal.
Like, share and subscribe. Hit the bell icon for more updates.